So we continue from where we had left off in the last class, in which we had defined what a shear stress is. So just to repeat it once more, the stress components parallel to the surface will be called shear stress. The shear stress components acting on the x face in the y direction will be identified as this tau x shear y, and this we have discussed before. What does this notation mean? This stress component acts on the x plane in the y direction. Okay, we have already discussed this before in this course. So the stress components perpendicular to the face will be called a normal stress. Okay, and they are shown by the sigma symbol sigma, and the normal stress components acting on the x face will act in the x direction, so this can also be written as sigma x. Okay, so though we don't write it, I mean we just write it like sigma x, because the normal stress will always have this script and this script as the same, so it will be either sigma yy or sigma zz. But just to be clear of the procedure, so this is how it is written. So now if we want to define what sigma xx is, okay, so that you would do by writing sigma, let me just write sigma x is equal to delta fx by delta ax for a limit of delta ax tending to 0. So this is how the normal stress acts. Similarly, you can write it for a shear stress, which is tau xy is equal to limit of delta ax tends to 0, where delta fy delta ax. Now please do not forget this figure. Okay, all these delta fx, delta ax and delta fz are found in this figure 4.5. okay, so please keep this in mind when you sort of write all this over here. And similarly, you can have a tau xz, which will be the limit of delta fz by delta ax, with the delta ax tending to 0. So all these three stress components which you have, so delta tau xz, I'm just writing like that, they are shown in this figure, which is 4.7. These are the components of the stress, okay, on the x plane, which in the x direction, I'm sorry, and this is how they are shown. So sigma xx is the normal stress acting perpendicular to the plane, tau xy and tau xz are acting parallel to the plane, and hence they are the shear stresses. Okay, now again the sign convention of this is the same as before, just like we had for the force before. The component is positive when a positively directed force component acts on a positive face. Okay, and then it's a negative in the other way around. So this is the same sign convention as before, so we are not going through this. Now if you return to the continuous body which was shown to us in figure 4.1, okay, this was the continuous body, figure 4.1. okay, we can also pass a plane. So what we have done right now is we passed a plane through this point, which was essentially YZ plane. Okay, MM was parallel to the YZ plane, so this is the YZ plane. Okay, so first was this MM which we had cut, and this was parallel to this YZ plane. Now what the author says in your textbook is that we can, in this figure, we can also pass a plane through O, obviously, which is parallel to the XY plane. Okay, so you can pass a plane which is parallel to this xy plane. You can also pass a plane which is parallel to the xz plane through the same point. So it might look something like this. It's a messy diagram, but I think you are able to see what I'm trying to say. Okay, so this is a plane which is parallel to the xz plane, and then you can have a third plane as well which is parallel to the xy plane. Now we have already done an analysis for a plane which is which is parallel to the yz plane, and we found out these three components, sigma x, tau xy and tau xz. If you repeat this analysis for the xy and the xz plane, in the sense now your will be parallel to the xz plane, and then your delta ay will be equal to delta x multiplied by delta z, and then you will have to do the same analysis as before. You will be able to get the state of stress. Okay, at point O. Okay, and this is analogous to what we have just done over here. This is 4.3. This gives you the sigma xx. Okay, tau xy, tau xz, tau yx, sigma y. So y. Now you see this was for the ax, delta ax. This will be for the delta ay, meaning a plane which is parallel to the xz plane, and this would be tau yz. Now the last will be for delta az, which is tau zx, tau zy, and sigma zz. So you have found these components of stress by using the same theory as before. So you end up with this total of 9 components. Now if you look at it closely, each line of this, okay, like this line and this line, so I will remove these lines just so that you don't start thinking this to be a determinant. Okay, we see that each line of 4.4, this is 4.4, this is 4.3, each line of 4.4 gives the component of the stress vector acting on the respective coordinate axis. Okay, so this line, for example, gives the components of the stress vector acting on the respective coordinate plane. Now how is that true? Remember, we had discussed this over here in this figure, that the stress vector must be written in terms of three vectors, okay, which are directed along the coordinate axis, and we had done this analysis for this one, okay, for the yz plane, and similar to can also be done for the xz and the xy planes. So this one vector now can be written in terms of these three vectors, and what you have over here is essentially the components of that stress vector along these directions. So this will be essentially I cap, j cap, and k cap. So the component of the stress vector Tn, which is directed along the x-axis, is sigma xx I cap, tau xy j cap, plus tau xz k cap. Okay, and similarly for the other two as well. Okay, so this is how the three vectors are written, and this collection of symbols which you have is just a way of writing them along these three convenient directions, and this is defined as the state of stress at a point O. Okay, meaning at this point O, the stress can be completely defined if you have all these 9 numbers with you. Okay, that's the meaning of state of stress at this point. Okay, a knowledge of the 9 components is necessary in order to determine the components of the stress vector acting on an arbitrarily plane with normal n. Okay, so this Tn, if you recall, this Tn was arbitrarily aligned, but now these 3 directions which you have taken, they are not arbitrary. Clearly the directions now are fixed. The normal vector acts perpendicular to these planes, which is yz, xz and xy. So so this infinite possibilities which you had, they can be, for the sake of convenience, be brought down into these 3 directions, well chosen directions of the coordinate system, and you have these numbers. Okay, now we will return to the relation between the components Tn and components 4.4 in the next section. We will see this is in slightly greater detail, how this Tn, which was the stress vector at a point along a particular orientation n, is related to these 9 components. This relationship we will explicitly see in section 4.5. Okay, the only difference is the n over here is arbitrary. Okay, so the plane with which you are making this cut at O, hypothetical cut at O, is arbitrary. In this case, the plane with which you are hypothetically cutting at the same point, okay, that is directed along the x-axis, y-axis and the z-axis. That is the difference between this and this. The relationship we'll see, okay, in the section 4.5. Now let's come back to the body of this 4.1 which we have seen. And now in addition to this plane MM, you pass another plane which is parallel to MM but separated from it by a small distance. So you have already passed a plane MM. Okay, let's see it over here. Okay, you pass another plane in this body, okay, which is parallel to this MM plane but separated by a distance delta x, so somewhere over here. Okay, this is also a plane parallel to this yz plane, MM plane, and it is separated by a distance x, small distance delta x. And similarly you can pass planes which are parallel to the xz axis at O, okay, at O, and then a plane which is separated by this distance delta z, and similarly the third plane which is the xy plane, and another plane which is separated by a distance delta z. Okay, I think in the earlier one it would be delta y. Xy xz parallel will be separated by distance delta y. Okay, now you do all that and now you see something like this. Let's see it in great detail. This is that 4.0, okay, over here. And so the plane MM was essentially this plane originally, what we have been considering. You have drawn another or cut another plane which is parallel to that and separated by delta x. Okay, these are the 2 planes. Similarly, you have at O the plane which is parallel to the xz plane, this one at the bottom, and it is separated by another plane which is parallel to this xz plane, separated by a distance delta y. And the same goes on for a third plane which is passing through O. It has to the first plane always has to cut through O. Okay, there's no doubt about it. And that's why this was your first plane, which was the xy plane. and now you have another plane, this one, which is parallel to the xy plane but separated by a distance delta z. Okay, so these are the planes which you have, and those are shown in this particular figure. So one thing which we will do is, very carefully we will note down the symbols, because there may be an error in the way symbols are written. Okay, so let's see if they are correct. So let's start with say this plane. Okay, this was what we already had, this in the YZ plane So sigma x is directed outside the plane. Okay, so this seems to be correct. Okay, and then you have tau xy as this. Okay, so it is in the x plane in the y direction, so that seems to be okay. And then you have tau xz, okay, which is shown on the x plane in the z direction, so that's also fine. Okay, now you see the plane which is parallel to this plane and separated by delta x. Sigma x is coming out of this plane, sigma x dash. So you will see this dash terms for all the symbols which are actually on the opposite plane. So without the prime symbol, it means it's the original plane, and with the prime symbol, it means it's a plane which is separated by the distance delta x, y, z, whatever. So sigma x dash is shown as a image of this one. Okay, so this is directed outside the plane, and sigma and tau dash xy is the same on the x plane in the y direction, and tau xz is again on the x plane in the z direction. So this and this is sorted. Okay, so let's look at the other term. Okay, let's take up another plane. Let's take up this one. Okay, so sigma y dash is directed on perpendicular to the y dash y direction. Okay, so that's sigma y dash, and look at this. This is on the y plane in the z direction, so this is not correct. Actually, I think you should make this correction in the book. This direction should be tau dash on what plane? On the y plane in the x direction. Okay, it was incorrectly written as tau dash yz, so this should be tau dash yx. And similarly, this particular one, so this one is correct. Okay, tau dash yz, because it is on the y something plane in the z direction. So this is correct. This is correct. Okay, so that's why you should be careful when you read the book. I mean, there may be misprints, typos, and so on. So only when you read it and clarify among yourselves, you will be able to find out errors like this. Okay, now let's check the one which was the original plane. I think we should have checked that before only, but anyways, so sigma y perpendicularly outside, it's okay. Tau yz on the y plane in the z direction, no, this is wrong. This should be tau yx. Okay, and this is tau yz, which is correct. This is correct. Okay, so please make these corrections in your textbook if I mean, if it's not already there for you. Okay, so let's now check the third one also, since it has been okay filled with errors, this figure. Okay, which one is left? What we are left out is the What we are left out with is this, sorry, is this plane now. Okay. So for that, let's look at this point. It's on this plane. Okay, the plane which is away from your screen. And sigma z is the component of this stress outside. So that's sigma z. Tau xz, let's see. Is this on the z plane? Yes, it is on z something plane. Oh, is it on the x plane? No, I think this is also incorrect. It is on, yeah, I think these symbols are not correct. So this in the this is wrong clearly, right? So this symbol must be tau y and on the z. So it must be zy. Okay. And similarly, this particular symbol must be zx. Okay. This must be tau zx. Okay. Now let's check this plane, the plane which is closest to us when you look at this. And this is the point of reference. So please make these corrections. I'm really sorry why this is like this in a book which is this old. But anyways, I think since we know how this notation works, we can note this. Okay. So that's the first part, and then let's look at this one. Okay, so sigma z dash seems to be okay, coming out of the screen, and then this one should be tau zx again. Okay, this is wrong, and this one this particular one should be tau z y. Okay, or dash, always with a dash, because this is opposite to the original plane. Okay, so please keep a note of this when you can always wind and rewind the video and see how we have arrived at this. Slightly messy, but I think it should be very clear once you yourselves are clear of how this is happening. Okay, so request you to make the corrections in the book only when you are convinced, and if you are not, please point out to me if you have any issue with this. Okay, now this is what we have done, and what I'll do now is I'll just remove these corrections from over here. Okay, or let me not move that corrections, just to I'll try another way to explain the next part. So one of the things which you notice is that the point O is actually this vertex of this cube or parallelepiped or whatever else you would want to call it. Okay, and but the stress values which we are taking on the faces are actually the centroid of those faces. I mean, you see this, okay, you see this, these are all the centroid of those faces. They are not actually point O. Okay, so this is how the symbols work, and one reason why we have shown this tau yx and tau dash yx by different symbols. So there's one with a prime, the other one is without a prime, is that they may not have the same magnitude. Okay, I mean, they are acting on different planes, though the planes are parallel, but there is no logic for them, at least from the theory until now, that they have to be equal, and that's why we are using these primed symbols, so that just to tell that tau xy can have a different value than tau dash xy, and the same would happen for, say, sigma z can have a different value than sigma z prime. Okay. Now in this figure 4.8, we assume that the stress components tau xy, okay, is uniform over the negative x phase. So the tau xy which you see over here, the assumption is that those stress components are uniform on that negative phase. Okay. The reason you can make this assumption, and so you can always say, well, we are actually violating this non-uniform motivation which we started this chapter. The reasoning is not so much. The reason is that it's a very small delta y, delta x, or delta z. So you can actually assume that tau xy on that face is the same. Okay, but as soon as you see tau x y dash, so where do you see tau xy dash? Let me just remove. Okay, this one. Okay, this is tau dash xy. This is tau xy. So tau dash xy will be uniform on the positive face, positive x face. Okay, that's true. Tau dash xy is positive, is uniform on the negative x face. Tau dash xy is uniform on the positive x face. But they have different values because they are separated by this delta x distance. Okay, so they will have some change over this distance. Okay, now the stress components of figure 4.a should be thought of as an average value over the respective phase. That's one thing which you can take, that if you have any phase and you see how many stress values on that phase, you see three stress values on that phase, like one perpendicular and one parallel, two parallel to the faces. So those three values are uniform, or sort of an average over that particular phase. So take this phase, which is the positive x phase, or okay, this phase. On this phase you will have a sigma x, you will have a tau xy, okay, sorry, sigma x dash, tau xy, and tau y, sorry, tau xz, sorry, yes, tau xz dash dash, just to show the plane. Now all these three values which you have are an average. This is an average over this phase only. Okay, so this is how you can see them, and that's why they are not varying from point to point on this phase. Okay, so this is what we have gone until this far. Now there is one more sort of way to write this, and that is in something called the index notation. We will not be using the notation in our course because I think it is more suited in advanced courses rather than this course, and it takes away the visualization aspect of stress and strain tensor. That's why I think it's better to write in the XYZ format, but you should still know what that symbol is. So if you replace x by 1, y by 2, and z by 3, you can write the normal stress in the x direction as sigma 11 as limit a1 tending to 0, delta f1 by delta a1. Okay, sigma 12 again will be written as limit of delta a1 tending to 0, delta f2 by delta a1, and so on. So you can write what sigma 31 is. Okay, that would be limit of delta a3 tending to 0, delta f1 divided by delta a3. Okay, so that's how you would write sigma 31. Okay, sigma 13 is already given in your book, so you can have a look at it. Okay, so as I've said, I mean, this notation we won't be using it, and in the more sort of general form, this can be written as sigma ij limit of A I tending to 0, delta F J by delta A I. Okay. So this is the shorthand form of the stress components of the stress vector which you have seen along the three directions. Okay, so three spaces. So do note that these three are actually components of a stress vector along three separate directions. They are all mutually perpendicular directions, but these are separate directions. So these three are individually stress vectors in themselves. Okay, so that's enough for the notations which we have studied this far. And before we move ahead, we want to make our life slightly simpler. That is through obviously an assumption, and you will see the basis of that assumption over here. Okay, so it's called a plane stress, and we'll see what it is. So in many instances which we see around us, the situation is actually much simpler than what you see in figure 4.8. Okay, I mean, part of the complication in figure 4.8 is because of the error which was there in the book. Okay, so but even when after having made those corrections, the situation is simpler than what it is in figure 4.8. Now, one way to look at this is this, that if we pull on a long thin wire, okay, notice the words very carefully, you are pulling a long thin wire of uniform section, and examine a small parallelepiped whose x-axis coincides with the axis of the wire, then sigma x and sigma dash x will be the only non-zero stress components acting on the faces of the parallelepiped, and it will be necessary for equilibrium that sigma x is the same as sigma x dash. Okay, now that's what you would have if you have a long thin wire. You will only have the axial component, which is the sigma x and sigma x dash component. There will be no other component, just because I mean there is practically no delta y or no delta z to talk of in that situation. Okay, so we don't want, so that's a three-dimensional situation theory which we have learned, and now this pulling of a thin long wire with a uniform section is sort of like a one-dimensional analysis. Okay, so you will only have sigma x and sigma x dash out of this 4.8 which you have, figure 4.8, and all the other components you will not see. How many in total? Well, a lot. I mean, 9 are there of the unprimed and 9 of the unprimed, 9 of the prime. So you have a total of 18 ones, and all those 18 ones have been reduced to only 2, which is sigma x and sigma x dash, nothing else. And because of equilibrium, sigma x and sigma x dash has to be the same. Okay, so if this is a long thin wire, you will have a sigma x and sigma x dash, and for equilibrium we say sigma x is same as sigma x dash. Now there is one small note which I would want to make here so that everything is fundamentally okay. We have learned before that for equilibrium the forces must balance. Okay, and but here you see that we are balancing somehow stress components, so fundamentally this definition is wrong. Okay, the correct definition is that you have to balance the forces, so sigma x must actually multiply by the area, this area. Okay, that then it becomes a force, and this must be equal to sigma x dash. Okay, and then it must be multiplied by this area, which is a. Okay, now since a is not equal to 0, or ax, whatever you want to call it, is not equal to 0, this then implies that sigma x is equal to sigma x dash. So this is one thing which you should be very clear. For equilibrium, it is not the stresses which must balance out each other, external stresses or whatever way you want to see. Okay, it is only the forces, and from forces you come out of this. And similarly, we'll see for rotational equilibrium, it will be the moments and not some other fancy word which we see over here. So this point should be very clear, that sigma x equal to sigma x dash for equilibrium is a sort of a deduction. It's not like uh, a direct law which you can put in for equilibrium. Okay. So that's the first part for a one-dimensional, this three-dimensional theory being reduced to one dimension. Let's look at a two-dimensional approximation, and that is what plane stress is. Another example of a practical interest is that of a thin sheet, okay? Thin sheet, which is assumed, it's a good approximation for a 2D. Everyone understands and has seen what a thin sheet is. If you have a doubt, you can hold the paper of your textbook or your notebook. That's is what a thin sheet looks like. Okay, the thickness of that is very small compared to the other dimensions of your page. Okay, so it is being pulled by forces in the plane of the sheet. Okay, so just try to pull I mean, don't tear your textbook or your notebook sheet, but if you pull the plate, thin plate, or this plane of piece of paper in the plane, so the forces have to act on the plane of this sheet, is what you are considering. Now you take the xy plane to be the plane of the sheet. Okay, please have a look at figure 4.9. Okay, in this xy plane is the plane of your sheet. So this delta z is actually very small compared to, sorry, the dimension of the sheet is very small in the z direction compared to the x and y direction. So you will have the components of stress sigma x dash and sigma x. You will have sigma y dash and sigma y. You will have tau xy. Okay, so it seems the directions over here are correct. Yeah, directions in this diagram seem to be correct. Okay, and similarly you will have tau z, sorry, okay, tau xy and tau xy and tau, okay, tau yx and no, I think the directions in this one are also let's see the plane at which they are acting. Hold on. Okay, so sigma x is okay, sigma x dash is this plane, is this stress component tau xy, it is acting on the x plane in the y direction, so it seems to be okay. Same has to apply over here. Okay, this is correct. Okay, now let's look at this top face of this, sigma y dash and sigma y. Okay, tau y dash in the x direction, correct. Tau y dash, okay, so this is tau yx. Okay, so that's the correction which you should make. Okay, lots of them today. Okay, so this is tau yx and everything else seems to be in order, and the idea is that if you have this 2D planes and you're planning to sort of pull it in the plane, the forces are applied in the plane of the paper, these are the only stress components which you will have in this parallel pipe. Some of the ones which you will be missing out are tau x z and the primed one. So I'm not writing the primed one separately. Tau yz, sigma z. Okay, so they will also have one primed one for each one of them. Okay, and you will also be missing out on tau zx, let me light them over here, tau zx, tau zy, and the ones, okay, so on. Okay, so this is not what you would be having, and the reason is the same as for the one-dimensional one. In one-dimensional case, you didn't have a considerable y or a z direction because it was a thin long wire, so the only prominent direction was in the x. In this one, you are able to ignore the z direction because the only prominent directions are x and y. Okay, so there is no delta z to speak of in this case, and hence there is no need for you to assume any other change in thickness, any variation of change in thickness. For example, sigma z is this normal stress in the z direction, and sigma z dash would be the normal change in the normal stress along the z directions on the opposite face. But since this delta z is negligible in this case, so you will just ignore the z component over there. So you ignore all the z components everywhere. So you end up with only a few terms, which is sigma x at a point. The state of stress in this case for a plane stress is tau xy, and then tau yx, and then sigma y. Okay, 4 components. Earlier you had 9, so you reduced it from 9 to 4. So this one is not there, 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 this one is not there. Okay, because all of them involved z. So we can assume, and again plane stress is not a condition, it's an assumption. Okay, it is not a condition that your paper is thin and or your sheet is thin so you can do this. It's an assumption that if this is thin, okay, you can assume that there is no variation in the stress components in the z direction, and hence you can ignore it. Okay, so that's how you take care of it. And we know that there is no variation in the z direction because I mean, since you all the forces or the pulling which you are doing is in the plane, so there is no question of a sigma z existing. Okay, since there is sigma z is 0, the sigma z dash will also be 0, and so on. Okay, so the stress components are functions of x and y only, and this combination of the stress field is called plane stress in the xy plane. It is illustrated in this figure 4.9, and there are many important problems in stress condition in which the plane stress is used, and you can examine some of the special cases as we move along in this course. Okay. So this is normally applied when you have a very thin solid. Okay, so for thin solids this works very well. Okay, so let's now move to this next topic, which is the equilibrium of a differential element in a plane stress condition. Okay, we are now moving with this assumption of plane stress in which we will only have some components. So I think we have to make some changes in this figure just for the corrections, and because we have learned our theory so well, I think we are in a good position to make those corrections. So let's start with this. You have a continuous body which is in equilibrium. Okay, one thing which they have told us is it is in equilibrium. Then any isolated part of the body must be acted upon by an equilibrium set of forces. Okay, so the body as a whole is equilibrium, and then individual parts, the smaller parts of this body are also in equilibrium. So you have taken a small element like this, okay, in figure 4.9 over there. Represents part of the body in plane stress, therefore must be in equilibrium if the entire body is to be in equilibrium. The requirements of equilibrium will establish certain conditions which must exist between the stress components. Okay, So there is a relationship between the stress components. In a one-dimensional case, we had seen that sigma x has to be the same as sigma x dash. So we'll now see for a plane stress in a 2D conditions what are the conditions, or what are the relationship between the stress components. And you don't have lots of stress components, only 4 to speak of. Okay, so let's see how that happens. Before we find, you shall express the stress components which are over here. So let's, going with this sort of hurricane of correcting the textbook, let's go through these notations once more. One thing which we'll do now is we will remove the primed components and include a small variation for it, and I'll show you how. So your original phase, so this is again point O, no change happens over there. Okay, sigma x is acting perpendicular to the plane. Okay, nothing wrong there. Now we want to go to sigma x dash. We write sigma x dash as sigma x plus dou sigma x by dou x into delta x. So this incorporates or sort of signifies the change which has happened coming from here to here in this value of sigma x. Okay, so that's the assumption which you are taking, and you can also write this using sort of a Taylor series. Okay, in Taylor series you will have lots of terms, the higher order terms will keep on coming, but you have clearly truncated it to the first value. So you know how that happens. So that is one way you can write it. So you have ignored the higher order terms and just written that the stress at this point, which is the average for this entire plane, is sigma x plus dou sigma x by dou x into delta x. Okay. So this is how it works. Now let's look at the other values as well. Sigma y, for example, that is written as sigma y, and this would be dou sigma y, dou sigma y plus dou sigma y by dou y into delta y. This seems to be correct. Okay. Now let's check the other values. So I'll just remove the ticks. Okay, let me keep the ticks on this ink where a correction is actually needed. Okay, let's see tau xy on the x plane in the y direction seems okay. Now tau dash xy is tau xy plus dou tau xy by dou x. Variation is in the x direction into delta x, so this is correct. Okay, now so these two faces seem to be okay. Now let's check with sigma y. We had checked, so let's start with tau y. Okay, so this is again not tau yz, this is on the y plane in the x direction, so this is tau yx. We have made this correction in over here as well, and hence this must be tau yx plus dou tau yx by dou y into delta y. So this is all wrong. Okay, so now we have written the stress and the increments of this once you move a certain distance from the original plane. Why am I calling a plane original and the other its copy? Because that original plane must pass through O. That is one convention which we have kept throughout. Okay, O is this point, and every plane which you see unprimed will always pass through that point. The other plane, though parallel to it, will not have those will not be passing through the point O. Okay, so that's how it is written. So we are following this partial derivative, and we write these terms. Now figure 4.10 is sort of corrected, and I think you should be making these corrections in your textbook. Okay, please do that, and do make those corrections in your textbook. Okay, so you now require this element which you see in this figure 4.10. The element which you see should be must satisfy the equilibrium conditions. And what are those equilibrium conditions? Sigma m is equal to 0 and sigma f is equal to 0. So to this element which you have artificially cut out using these 6 planes, okay, all these stress components will result in forces which are actually external. Okay, so the internal forces have been converted to external, just like we have done in chapter 3 as well, by hypothetically cutting, and the same has to be applied. So for sigma m equal to 0 and sigma f equal to 0. So sigma m equal to 0 is satisfied by taking moments about the center of the element. So consider the centroid of this element, the center of this element, and see if you can write delta m. So we must be very careful over here, just because I don't think, let's check what is written in your textbook and see whether it's correct. So we first want to write the sigma m equal to 0. So all the forces clearly which you have, all the forces which will result for the stresses which you have, will be in the plane xy. Okay, so the moment has to be in the z direction, in the k direction. So let's start one step at a time. Let's start with tau xy. Okay, where is tau xy? It's over here. So what is the force contribution due to this? You will multiply tau xy with the area, which is this area, which is delta y into delta z. Okay, that becomes a force now. And so what is the lever arm for the center of the this parallelepiped? Okay, that will be delta x by 2. Okay, fine. So the first part is done. Now we must write the second term. Let the second term be this tau xy, this one. Okay, so tau xy plus dou tau xy dou x into delta x. This multiplied by the area. What should be the area? Delta y delta z again. And this has to have a lever arm which is delta x by 2. Okay, that's the first thing. Now both of these are shown with a positive sign r cross f because they are in the positive z direction. Okay, now the shear stress, this one tau yx, the lever arm of this will actually point to a moment which is then in the negative z direction. So we'll put a negative tau yz. What should be the area of this plane? Delta x into delta z, this plane, the bottom plane, delta x into delta z, and the lever arm should be delta y by 2. Okay, similarly you will have for this particular shear stress, the force. How will you calculate the force? Write the stress. Okay, and then multiply by the area. What would be the area? Delta x into delta z. What would be the lever arm? Delta y by 2. Okay, and all this will apply in the k cap direction. That must be equal to 0. Okay, so it seems the only the diagrams in the textbook are wrong, but the formulas in the theory is all correct. Okay, very surprising. It's a very old book. Okay, anyways, we have found out the error, so nothing can challenge us anymore. Okay, king of the world. Fine. This is the first condition which you have sort of satisfied. And now then the second condition, delta f equal to 0, also has to be written. So what I'll do is I'll just write this as 4.8 and remove this because it's given in your textbook. Okay, and I'll just so that I have space for writing delta f. Okay, and this you would do. There are only two directions of relevance. One is sigma fx. So what are the forces lying in the sigma fx direction? One is this one. So sigma x plus dou sigma x by dou x delta x. What is the area with which we must multiply? Delta y into delta z plus what are the other forces in the x direction? Clearly this one. Okay, you see the arrow of it. The arrow gives all the answers. That would be tau yx plus dou tau yx by dou y, okay, into delta y. You should multiply this by the area, which is delta x into delta z. And then in the negative x direction, what are the forces? One is sigma x itself, sigma x delta y into delta z, that makes this as the force, minus tau yx delta x into delta z equal to 0. Okay. So this becomes equation 4.9, and similarly you can write a sigma fy equal to 0. I'm not writing, you can check your textbook. By the trend which has been going on, it seems they'll be correct. Okay, and that's how you write sigma fx equal to 0 and sigma fy equal to 0 in these cases. So you have equation 4.9 and 4.10 for the force equilibrium. Now they say that you are simplifying 4.8. And how do you simplify equation 4.8? You can just divide it by, say, delta z and delta y. So you look into your textbook. Okay, it is written that simplifying equation 4.8 you will get something. So that simplification has happened by dividing both sides by certain terms. So let's see whether we can actually do that. Okay, there are these higher order terms which you can clearly ignore. Okay, so that is gone out. So tau xy will be there. Okay, and delta x. Okay, you can take this common and you will be able to get this. Okay, so you should get equation 4.11 after you do this. Very easy to simplify, and that you should get as tau x delta x by 2 minus tau yx minus dou tau yx by dou y delta y by 2 equal to 0. Okay, so now as delta x and delta y tend to 0, okay, you will notice something interesting, and that part would be that tau xy will be equal to tau yx. When delta x tends to 0, this entire term will tend to 0. Similarly, when delta y will tend to 0, this entire term will tend to 0. And that's why you are left out with tau xy equal to tau yx. This result shown by 4.12 is of great importance in the study of stress at a point. Okay, because it tells you that the shear stresses are actually symmetric. Okay, so tau xy is the same as tau yx. So we have made this proof for a plane stress. Remember, this was plane stress. Okay, so tau xy is the same as, so we had this 1 2 3 4 components remaining, and even that we have reduced to 3 now, because tau xy is the same as tau yx. But the point to be made over here, that this equation actually 4.12 is true for any state of stress at a point. So if you prove this, do this moment balance, if you do this in the most general case, okay, then you will be able to show that this is true not just for plane stress but in the most general case. Okay, and the way we have done it, sigma m has to be equal to 0. The moment around the center has to be equal to 0. Okay, so you can also, in a 3-dimension case, the proof which we are not doing right now, because at this level plane stress proof is okay, but the point is that when you have this sigma x tau x y, where did we write that? Let's see, over here. Okay, over here, let's go back to over here and let me use another pen. Okay, so tau xy has been shown to be equal to tau yx. Similarly, it is easy to prove, not we are not doing it because of it's slightly more involved, but it is possible to prove that let me write with another pen. Tau zx will also be the same as tau xz, and another pen, which one should I go with? Let's go with brown. Tau yz will be the same as tau zy. So the 9 components which you had for the state of stress in a general 3-dimensional case would actually be reduced to 6. Okay, 1 2 3 and 4 5 and 6, because the other 3 are the same. So that is what is shown by this moment balance. So if you are ever asked why are the shear components of stress same or equal, the answer is because the moments have been balanced for the equilibrium, for the sake of equilibrium. Okay, so that's what we do, and let's stop this class over here and we'll continue from the next class. Thank you.